Swayam Prabha. Digital India. Educated India.
So that is to, okay, now the topic that I have looked at is something called antimicrobial resistance. Antimicrobial resistance is a very, very important problem. As you know, when we get sick, we get antibiotics, but the antibiotics don't work all the time because this microbes, bacterium, they also develop some sort of resistance, and many times you actually make a mixture of many antibiotics and you do, and bacteria also smart, they can also detect and then sense. So the idea is, how do we understand the action of antibiotic on the microbes, and also how microbes are actually even destroying the drug itself. So it's a very complicated reaction network. You can do it in a well-mixed system, you can do it in a spatially distributed system. There are a lot of combinations are possible. Typically these are a model using a deterministic approach, but a lot of data is coming up experimentally where people have looked at single cell data and you see a lot of fluctuations about it, okay, and that's a nice domain where stochastic modeling can be useful, right? So I'm going to actually kind of upload a set of papers, all of them on AMR, antimicrobial resistance, but the modeling framework can be different, very simple, very sophisticated, and depending upon what questions that we would like to ask. So I expect you to kind of go through the list of paper, pick the one that you find interested, and then start working on it. And I will also probably have one-to-one discussion before you start the project, just to be sure that you know what you're getting into it. So the ultimate aim of that project is to see whatever we have discussed in the class is something that is applicable. Okay, generally we do course and we get a grade and then we move on. But I think this course is different, and I want all these concepts to be applied somewhere. Okay, like I said, you can also take it beyond the course if you want. Okay, so that's the expectation from my side. Any thoughts on that? Any questions?
So how do you ensure that you have to take different papers?
I'm going to upload several papers.
But if two of us take the same,
that's fine. That's fine. But it's going to be an independent project. You're going to look at the paper differently. Maybe you're going to reproduce some results, maybe easier ones. Maybe there's other student who's taking the same paper may actually do benchmark other papers. So when I do one-to-one interaction, I'll probably know who is doing that project, who has selected that paper. If there are more than one, I will probably tell them, look, this person is already doing this, so don't do that, do something else. So that kind of hand-holding we will do. Yeah? Any other concern? All right, so okay, we'll get to the stuff. So first we will do what's called recall. And so we say a Markov process is fully defined by two things, right? One is you need to know what is this P1 of x1 comma t. So this is called the single point distribution. In other words, this is basically the initial condition, if you like. And the second is the transition probability. So here, this x1 here is the variable that describes the state of the system. And this can be a scalar or it can be a vector also. It can be a single component or it can be multi-component. And this is the natural time. So at time t, what is the probability the system will be at state x1? That's what this is, okay? So you want to initialize this process with some sort of a initial condition, okay? So that is needed. The second is, we also describe this transition probability when the system is at xn minus 1 at tn minus 1, and the next time interval tn, it goes to xn minus 1 to xn. That's called the transition probability. right? So here we see that it does not depend on the state at Tn-2, Tn-3, Tn-4 and all that. It just depends only on the previous state to move to the current state, right? So those are the two important aspects that characterizes the Markov process, right? And once we have this, we also wrote the Markov property. Suppose if I want to calculate the trajectory probability of xn tn xn minus 1 tn minus 1 all the way up to so you can see that this kind of encodes, this is a joint distribution, right? This is joint probability distribution. It kind of tells me what's the probability of finding a trajectory which is characterized by x1 t1, x2 t2, x3 t3 all the way up to x1 tn. This suffix n here means how many number of arguments are here, trajectory points, okay? This is something we wrote as p1 of x comma 1 t1 So when we have this transition probability defined, then we can create a joint distribution function of any length starting from the initial distribution function times the probability of successive probability. Okay? We have seen all these things. Okay. Now, this kind of defines the properties of Markov process and how we manage this with a transition probability. Any trajectory length can be generated through this. Okay. So now, subsequent to this, what we did was we wrote a differential equation for the transition probability. We call them as a chemical master equation. Okay. Chemical master equation is basically a differential equation whose solution will give you the transition probability. Okay. So for example, I think if I look at one example which we again discussed before, if I have one-sided random walk, we got the solution. This is a solution that we obtained from the differential equation, which is a chemical master equation. So we got something like e power minus a If you go back to your notes, you will see that for one-dimensional, one-sided random walk, we would have written the chemical master equation, then we used generating function, and then we obtain analytical solution, where it is kind of a Poisson random variable. Okay, so from here, once you have the transition probability, this is a transition probability. We can also write the single point distribution at any time t, the probability to find x, given that at time t equal to 0, x equal to 0, this is something written as a t power x by x factorial. So we have got all the necessary information. So from here onwards, I can get all the statistical property, mean values of x, standard deviation, coefficient of variation, third moment, fourth moment, whatever we want, we can get it, right? So, so all the moments can be obtained from here, or else there is another tutorial session we did where we wrote a small Python code where we use this transition probability to create numerically to create the trajectories. You can create as many trajectories as you want. You have an initial condition, take a small time delta t, and using this distribution, you find what is the probability to jump to a certain distance. Okay. So you actually created many number of, how many of you did that in the class? I think there was a tutorial where you were actually asked to bring your laptop and create this trajectories. We did this one or the reaction? Okay, okay, maybe you would have done the reaction where you had a binomial distribution, but I also asked them to do Poisson also. The idea is you start with the initial condition of at time t equal to 0, x equal to 0, choose a small delta t, okay, and then from here you generate a new x value, and then you update the state of the system, and then from that point again create another random variable for the incremental value of x, and you keep doing this to get a trajectory. You can create as many trajectories as you want, and then at any given time t, you got sample point from each of the trajectory from which you can get the averages and standard deviation. Okay, so the point I'm trying to say here is that this knowledge of the transition probability allows us to create trajectories itself from which you can get the statistical property, or you can also get directly from this distribution function also. Okay, these are the things we have already done. Now this approach is good as long as you have a much simpler problem to solve. For example, here if you look at all the problem we have done with the chemical master equation, it would be either it would all be a discrete state where the state variable changes in an integer value, and the second is we have only one variable to talk about. When we have A to B, we dealt with only number of A molecule, because if I know number of A molecule, we will know what is the number of B molecule, because the number has to conserve. Similarly, in the one-dimensional random walk, there is only one variable. But in many reality situations, like for example, you are going to, let's say, model this antimicrobial resistance or gene expression. In these cases, you have multiple reactions happening parallelly, and we want to track multiple species at the same time. And imagine if you want to write a chemical master equation with multiple states, you can write it up, but then solving it analytically to get this kind of equation is going to be very hard. So we said that either you can numerically solve. I think we had another tutorial on that. Didn't we have that? Solving chemical master equation numerically using Euler's method? Yeah? So you can do that. Now what we are saying is, again, we are talking about multiple possibilities. Okay, now it's up to you as a user how you want to do it, what is something convenient for you. So now what we can do, when we have a very complex situation, multiple variables, discrete states, we have a different way of doing the same thing. Okay, and that's what we are going to talk about as Markov chain. So before I discuss the theory and the details, I'll start with an example so we all understand what this means, and then we try to generalize to different problems. Okay. So we will take the example of a reversible reaction A going to B, because we know what the answer is going to be for that. So what we are talking about is Markov chain. Again, Markov chain is not a new concept. It is an old Markov process as we know. It is only a different way of solving the problem. Okay, it's a different technique to solve. That's all. So let's say we have a reaction A going to be reversibly. Okay, and we say that rate constants are K1, K2, right? And here we want to have the state variable as Na and Nb. Okay, basically we are interested in calculating the number of molecules of A, number of molecules of B as a function of time. So the system state is now described by two variables here, Na and Nb. Okay, we have done this problem using chemical master equation by treating only a single variable, and we know the other one, but now we are explicitly having both of them. And so if you see this reaction, A molecule can actually convert into B, and B can also convert back into A. So that's a kind of a physics of the problem. And we can actually think about an initial condition that is something like Na naught and Nb naught, right? So in this case, what we will do is we note that Na and Nb, these are random variable describing the state of the system, are discrete or discrete variables. Okay, and second is, even though time is continuous, we also discretize the time also. Okay, so time is discretized like 0, delta t, 2 delta t, and so on. Okay, so we keep delta t something frozen fixed, and then you look at the system's evolution from 0, delta t, 2 delta t, and so on. Or equivalently, we can say that the time is denoted by a variable m, which can take value m is equal to 0, 1, 2, 3, and so on. So when m equal to 0, that means time t equal to 0. When m equal to 1, it's delta t. Okay, so we have to just multiply m with the delta t, you know, the dimensional time. Okay, just to make things a little easy for us. Then we ideally want to write this p of x comma t. Okay, this is a probability to find the system at state x. X has two components at time t. Okay, so this we are going to write slightly differently. We will write this as p of m So here we are doing a notation change. We are used to this kind of a notation that at time t the state variable is described, and we are asking what's the probability that at time t the system can be found in the random variable x. X can be a scalar vector, in this case it's a 2 component vector. Now we are going to write this as separately as p of m. So in here I'm replacing time with m. Okay. Now this probability is now actually composed into 2 parts. The one part is the probability of finding the state at state A, and another one at state B. So this will be the probability to find state A. This will be the probability to find state B at those times. Okay. So we are kind of changing the notation a little bit like this. We are writing the state as a row vector. Okay. And the second thing we are going to do is the transition probability that we used to write, right? So I'll say this transition probability we used to write p of 1 comma 1 xn tn xn minus 1 tn minus 1. Okay, this is how we write the transition probability. Okay, now this I'm going to rewrite slightly differently. We write this as, in this case, as a matrix of PAA, PAB, PBA. Here I have only 2 states. Okay, the species is either A is possible or B is possible. So here this transition matrix that we write as a analytical expression of this kind, I'm going to write explicitly into a matrix form where there are 2 states. I say what's the transition from A to A to B, B to A, and B to B. So this A to B refers to the transition from A to B. Okay. Similarly, this B to A refers to the backward reaction. Now this AA is the probability that it will not react. Okay, remember when I take a small delta time delta t, there is a probability to react to B, and that probability is not always 1, it is less than 1. So if you ask 1 minus of that probability, that's a probability that the system will not react. So that's what I call as PAA. Okay, so what we know, what we understand as the transition probability is now written in terms of a matrix form. So now we need to know how to write these equations. So now I propose that the probability of the forward reaction A to B is, for a very small time delta t, I propose this is k1 times delta t. Okay, if I choose a time delta t small enough, the probability that one molecule A will react to become B is k1 delta t. So therefore BAA will be 1 minus PAB, which is nothing but 1 minus k1 delta t. Similarly, PBA is k2 delta t, and PBB right. So we can write this matrix then 1 minus k1 delta t, K1 delta T, K2 delta T, like this.
It will depend on MA and NG.
Sorry?
K1 MA.
No, so here we are talking about more like very very small delta time, delta T, only one reaction can happen. So I'm proposing that this is independent of the state of the system right now. Okay, so we have to discuss separately how to set up these transition probabilities. Okay, so in this example, I'm proposing this as the rates. Okay, so I've got so now what I need is the initial distribution function, then I have the transition probability, then I should be able to generate the state of the system over time. Okay, so I write that P of 1 is equal to P of 0 into T of 0. Okay, so P of 0 is at time t equal to 0, that is m is equal to 0. We have, let's say we started with Na naught is some 10 molecule, and let's say Nb naught is some 0 molecule. Okay, now the system is completely found only in state A. Okay, so the probability of state A is 1 and the probability of state B is 0. So initially only A is present, B is not present. The number of molecules I have given, but what is important is what's the probability of finding the initial state. The initial state is found with the probability of 1 at state A and state B is 0. Suppose if I have 5 molecule here, 5 molecule there, it will be 0.5 and 0.5. So the number fraction, the probability fraction will be accordingly scaled. Okay, so here we start with, let's say 1, 0. Now I want to operate this this probability. So here I need to find, so I need to choose some values here. Okay, I need to know what is K1, K2. So I will say K1 is 2, K2 is 5, and delta T is 0.1. I'm just taking some random example here, right? So if you see K1 times delta T is 0.2, and 1 minus 0.2 is 0.8. Here K1 delta T, that is 0.2. This one would be 0.5 each. See, I have chosen this example such a way that the transition probability is independent of time, independent of the current state. It doesn't depend on the N1 and N2. It doesn't depend on NA and NB. Okay, so that's easy. Later on, as you were saying, that if I bring this number of molecules in this picture, then each time this transition probability will also evolve. So right now we have a static transition probability. Okay, the transition probability matrix does not depend on the system state. Okay, it's always a constant. So now we can operate this. So when you do P of 1, you multiply this plus this, you will get 0.8. Like I said before, that if the transition probability also depends on, let's say, N1 and N2, and N1 and N2 is going to keep changing with respect to time. Okay, so right now to make them, I'm trying to highlight the idea that how we do this. Later on when we go to more actual situations, we'll bring all the other complexity. So right now I'm taking a very simple example where the transition matrix is constant in time, constant of the, it doesn't change the, it doesn't depend on the system state. So when you operate this, okay, you see initially the system was with a property of 1 at state A and 0 at state B. After one time interval, when m equal to 1, you have taken some delta t, 0.1. Now the system has gone to a state of 0.8 and 0.2. If the total number of molecules is always 10, which is fixed, you would actually have got 8 molecules of A and 2 molecules of B after one reaction. Now let's say you want to go to P2, next time step. So you write P2 is equal to P1 times T of 1. See, what I'm doing here is nothing but how I wrote the initial recursive relation for the Markov process, right, from the initial condition onwards. So I'm just doing the same thing. So here you would write 0.8, 0.2, and then this is the same matrix before. Okay, so if you do this, so 0.8 into 0.8 plus 0.2 into 0.5, you will get something like 0.74 and 0.26. So you can see the probability of finding state A decreases from 1 to 0.8, 0.8 to 0.74. Okay, but you know this is a reversible reaction. You would expect that this will go to an equilibrium, right? So if I do this over and over, I think by the time you do the 6th or 7th iteration, you will see this number becomes converged. It doesn't change anymore. Okay, so you get an equilibrium distribution of the probabilities. Okay, so if you continue this, if there is any question, you can ask me. So my others can also help. Yeah.
We are just doing a recursion, so it will be instead will be P naught into T naught to the power n.
Exactly.
T is not.
Exactly. Yeah. So I not put that formula yet. I want that to evolve. Okay. So yeah, you're right. Yeah. Sorry.
Markov chain, the chain is what?
The recursive thing is what called chain. Yeah. Because it is, so what is a chain? Chain is going from one state to the other in a continuous fashion, right? So here we are taking state 1, we are actually going to state 2 and then state 3 in a more like a sequential form, and that's why the chain comes from. So if you do this, I think I did up to P of 8 steps, and I got a value which is about 0.714 and 0.286, something like that. So you can see it adds up to 1, as it should, right? Because the sum of the probabilities, the system can either be in A, system A or system B, and the sum of them should be equal to 1, and that's what we see. Okay. So now we can say, okay, does it make sense? Okay, can we validate this? Okay. So to validate this, what we can do is we can go back to the deterministic way of looking at this problem, right? So I write that DCA, the phenomenological kinetic rate equation we write as K1CA plus K2CB. Okay, and then at equilibrium, this is set to 0. So we say that CS star, the equilibrium value of A should be CB star times K2 by K1, right? And if I define the equilibrium constant K as K1 by K2, then I have got CS star is equal to CB star by K, right? So now what I can do is I can write CB star as some C naught minus CS star over K, right? And then so if you solve for CS star, you will get C naught plus 1 plus K, right? So what is K for this problem? So K is K1 by K2. K1 is 2 and K2 is 5, so 0.4, right? So when you substitute this here, you get CA star is equal to 0.714 C naught. So the concentration of A at equilibrium is going to be 71.4% of the initial concentration. So here we written in terms of concentration, but if you think about this as a reactor with a constant volume, you can also say in terms of number of molecules, right? The number of molecules of A is equal to 0.714 times N naught. And from here we also know that NB star should be 0.286 N naught. So from the deterministic formulations, we know that the equilibrium concentration of A and B, or the number of molecules of A and B, should follow this, because we have chosen the constant rate constant K. Now coming back to this problem, what we did with this recursive Markov chain approach, we exactly predicted that here. Okay, so therefore we say that it's consistent and it's validated. Okay, so now you can also choose different k1 values, k2 values, right? And then you can do this over, and then you will see convergence to different equilibrium state depending upon the k values that you choose, right?
Static Markov chain.
Yeah, it's a static. Yeah, because the transition probability matrix, it doesn't change with the system. Yeah, but there are more general case where things need not go to an equilibrium state. It can come to an end state. Maybe one of the molecule becomes exhausted, so no further, more like a dead state. So this is a very, very important idea, because you can actually, I will show later on many such examples. Spatially distributed systems and multi-component systems can be handled in this kind of formulations. Okay, so here we have shown only 2 states. If I have n state, I would have n by n. Okay, I will have n by n matrix for the transition matrix. Okay, then computationally, then you have to do this matrix multiplication every time. Okay, so that's going to add some computational time. Okay, but other words, this process is very intuitive, because here we start from one state and then we operate with the transition matrix, go to the next state and then do over, like how we actually integrate differential equation in a recursive way, right? We start with time t, take delta t, discretize the equation, update state, and then do over in a for loop or in a continuous loop. The same way we are actually doing it here also.
This is similar to that Chapman equation, right?
Exactly.
What kind of Chapman?
Exactly. Actually, the way I wrote here is actually another form of the Chapman-Kolmogorov equation, which I initially discussed in there somewhere. Okay, so that's why you could also say that, as you mentioned, that P of m can be P of 0 t power m. You can do that. Yeah. So.
Who will they find the transfer function to experiment their thing?
No, so that is where, as a modeler, that's where our job comes in. Okay, so that we have to argue, we have to hypothesize that how do we describe this process, how to define transition probabilities, and that's where our modeling effort comes in. Okay, that's where human intervention comes. Otherwise, it's all automated, right? So we'll discuss that aspect when we talk about different examples. So here, as you see here, I have written in terms of all probabilities, but actually what you could do, you can even replace this with the initial number of distribution also. Okay, because these are all fractions. The probabilities are nothing but the fractions. Okay, so here you could have actually started with suppose if we say n is a random variable, that tells you the number of molecules to describe the system state. I can start with like this. So I would have started from 10 and 0. Okay, and I would have got here 8 and 2. I'm changing the probability into a number of molecules. So here I would have actually started with 8 and 2. You would have got 7.4, 2.6, and then when you continue this at equilibrium, you would have got this, which is what you would have predicted here also. So here in the Markov chain, you can directly relate the probabilities of the system to the number of molecules in this particular case. Okay. So later on, there is going to be a little bit of a problem when we go from one example to the other example, because how we are going to discuss the state of the system, how we are going to go from a real variable to the probability. Those are the things that we're going to discuss later. But for now, I wanted to kind of digest this, and in the next class, I will kind of formally introduce the theory of Markov process. If you understand this, when I write those equations for the definition of Markov chain, it will be clear to you. And from there onwards, we will apply for more and more problems, like I said before, grinding problems, size reduction problems, reactions, plug flow, CSTR, and complex reaction networks. There's a whole lot of chemical engineering problems we can attack with this. And it's actually more easy. I mean, you don't need a lot of theoretical sound basis for this. All you need to know how to set up my transition probability matrix. Once I know that, and again, that depends on subjectively how we model the problem, what are the things we have to factor in, how simple we want to make it, or what are the questions we are asking. Based on that, we have to construct the transition probability. Once you have that, then it is all recursive relations. You can just predict the state of the system as a function of time. You can plot, you can calculate the statistical quantities, and so on. Okay. So in a way, Markov chain is more like a numerical way of solving the Markov process. Okay. Only thing here we are saying is the states are discrete, and the time is also discrete. You see, time doesn't come in directly. Only it comes from one state to the other state. Okay. When I say P1, P2, P3, or N1, N2, N3, I'm going from different states, and I should know what one means, what delta t means. Okay. So we are looking at discretized time, discretized states. Okay. Under that condition, you can do this. In fact, even if the Markov process is continuous, even if the time is continuous, you can always discretize. And that's what we do with solving ODEs and PDEs. The space and times are continuous, but still we discretize and do it, right? The same way we can also do this. Okay. Think about this Markov chain as a numerical way of solving the stochastic problem. And towards the end of the course, I'm also going to discuss something called kinetic Monte Carlo, which is another kind of numerical methods. Okay. I know that it can be very confusing because I'm talking about various concepts, but I think maybe towards the end of the course, when you look the entire course material at once, you might be able to see why we did what and how things are related. Okay. I want to give all these ideas because depending upon what project you want to do, one method may be more easier than the others. Okay. So you have a lot of choices to make. Okay. You have a repertoire of many techniques and use the one that you think most suited. Okay. All right. I'll stop here.